Okay, well, thank you to the organizers and for the invitation and for making this possible despite the weird circumstances. And thanks to Reuven, that was a really great talk that touched on a lot of things that I'll discuss here. So first and foremost, I'll be talking only about the kinds of recoils that Reuven mentioned in the second half of his talk. So this is a completely different set of excesses unrelated to the recent excitement over xenon 1 ton, which is itself very exciting, based on a paper from February with my great collaborators Noah Kerensky, Dan Baxter, and Yoni Khan. So this is two experimentalists and two theorists. And this was published just yesterday in PhysRevD. I want to give you three take-home messages before we go in any further. One is, as Reuven alluded to earlier, is that there are many sub-GeV direct detection excesses driven by the great progress that this community has made over the past 10 years. We're learning a lot, and that's come about in a very complicated way. There's a candidate process to explain what these things are under the umbrella of a consistent interpretation of what all of these excesses are, and that candidate process can arise through dark matter interactions with detector material in a couple of ways that I'll discuss. So let's just dive into the first part. Unlike traditional nuclear recoil direct detection, experiments to probe sub-GeV dark matter typically involve scattering off electrons or through interactions with phonons, things that have smaller energy levels that can be exploited. And this is very prominently displayed here. This is a plot from CDMS high voltage where we can get very, very precise counts of how many electrons are deposited inside of a detector. Where the name of the game is to measure ionization and can now get down to single electron sensitivity, which is a huge accomplishment, particularly compared to what people used to think was possible in this game. But there's one important qualitative difference between doing this and what we're used to on the heavier end when we think about WIMP searches. And for WIMP searches, we have typically, if we're thinking about elastic recoils, an exponentially falling background and some threshold. And so we never have a meaningful measure of the total event rate. We only have a measure of the total event rate above some threshold, and it's exponentially sensitive to that threshold. So it wouldn't make sense to talk about total event rates across a number of different experiments, because even small differences in where that threshold is placed and certain kinds of detection efficiencies would dramatically change what the total number is, so it's not particularly meaningful. But in the case of these experiments, for the very first time in history, it's possible to talk about a total event rate because you can get down to very, very, very low thresholds. And so you can now say, well, what's the total event rate across a number of charge collection experiments, which is not necessarily what you could do with other kinds of techniques. So that's very exciting. And it gives us another independent probe of whether or not dark matter could be responsible for a given signal event, because that's not something that we would be expecting to change across different experiments despite their differences in detection strategies. So we'll jump right into it. There are multiple excesses across a number of different experiments. So as of 2019, this was the situation with SENSEI. You have an experiment that operates about 100 meters underground at 100 Kelvin temperature. And based on 2019 results from the PRL cited here at the bottom, there's an excess rate above expectation that was in the many to few hundred hertz per kilogram. This is the total event rate. And this has been updated, as Reuven mentioned. Reuven, of course, is a member of SENSEI. That this was updated in April of 2020 to be revised down to some extent. So now the event rate is somewhere between about 0.01 to about 1 hertz per kilogram. And we did just hear that there might be a new SENSEI paper offering an interpretation of this that does not involve dark matter. So we eagerly await that. But this is not something that we've heard about yet, so I can't comment on the claim from the previous talk, but we very eagerly await to see what happens. So you should keep an asterisk on everything that I say from here on out about SENSEI, because I'm only going based on publicly available information. But you also see this, or something analogous, if you look at, say, CDMS high voltage, which is a charge readout search based on similar strategy. So here, what we're dealing with is also silicon-based. You're looking at a comparison between Monte Carlo simulations in the red curves of known backgrounds that can be contributing to ionization, and then the pink curves, the pink histograms are the data, and you can see it goes way beyond what the Monte Carlo seems to be suggesting. Here we're dealing with a very different detector depth, very different temperature, very different experimental details, albeit the same material. And what's observed is something like 10 to a few thousand hertz per kilogram, with or without including the 1 electron bin. So if you think the 1 electron bin is perhaps more susceptible to backgrounds, then you should be thinking about the more reliable number as being on the lower end of this. And so we're thinking in the few to tens of hertz per kilogram to characterize this excess. Something similar is true for Edelweiss. If you look at their charge readout results, here we're operating under 2 kilometer depth at a 10 millikelvin temperature with a very different exposure, and there's still an excess that's broadly compatible with the same caveat about including versus not including the first 1 electron bin, where you get something that's in the ballpark of order 10 hertz per kilogram on the lower end versus something in the 100 hertz per kilogram if you include the higher one. But of course, one thing that would give small differences between these semiconductor results is that here we're dealing with germanium, whereas SENSEI and CDMS were dealing with silicon. So we wouldn't expect the rate to be exactly the same, but we should expect it to be the same for a given material. So that's something important to keep in mind. Now for DAMIC, here the situation's a little bit different. So DAMIC is in some sense the outlier if you take at face value the analysis from the PRL from 2019, reporting a low dark count of about 10 to the minus 3 hertz per kilogram. But there are a couple of caveats about this. Of course, there's nothing wrong with this claim. This is a perfectly reasonable claim. But one thing to keep in mind is that they use a different ionization model relative to the other experiments, at least in that 2019 PRL. And the dark counts number is based on a likelihood analysis, which is also somewhat different from what the other experiments use. And that has a prior, namely that the events that are observed are treated as dark counts, and it could potentially misattribute a would-be signal if the prior were different. And so a different interpretation would be that if you just look at the counts that they get per unit area per day, this could be as high as about a few hertz per kilogram. Again, this is specifically related to a different interpretation. And so if you just look at semiconductors, you see an intriguing pattern, and it could, of course, just be a coincidence, but it's notable that for lots of different depths, shielding, exposures, detector composition, temperature, and pressure, the more reliable of these event rates, the ones that are on the lower end of what you're seeing in that column there, all roughly align with each other. Keeping in mind, of course, the caveat about DAMIC. And this is, by the way, a screenshot of a table that we had in our paper from February, so that does not include the more recent SENSEI results, so just keep that in mind. But I wanted them all to be up here as it's presented in that paper so that we can see them side by side, because that's the interesting coincidence in all of this. But of course, there are other experiments that have something to say about dark matter below the GeV scale. And these involve more traditional kinds of readouts. So for example, if you look at the middle section here involving traditional nuclear recoil searches, these are much higher threshold. And because of what I mentioned earlier, since you have to impose a threshold on these that's much higher and typically very different, the total event rate is not something that you can compare in an apples-to-apples way. What you can say is that that gives you a lower bound, and that you would expect the overall event rate to be higher. But now you're potentially dealing with the possibility that this is from a different interaction, because we're dealing potentially with charge readout versus energy deposition, or In the case of the bottom section, where we're dealing with photoelectron readout, you're dealing with a totally different detection strategy as well, and a different set of thresholds. It's hard to compare the energy readout section because the total rate's not known. It's important to note that Xenon 10, which does measure the total rate, does see a smaller excess. That Xenon 10, 100, and 1 ton also intriguingly have similar rates if you were to impose similar thresholds for these. So this is interesting to keep in mind. But what I really want to focus on for the rest of the talk as a vehicle for comparing these is that if you look at EDELWEISS, the germanium readout, the germanium target experiment, there are runs at different depths involving both charge readout and just regular calorimetric readout, and both have excesses. And they both have fairly large excesses. And what we can do is see whether or not these can be put on equal footing, because we do have a way of translating for the same experiment, for very similar detectors in both runs, what a energy deposition event would look like if you were to observe it and interpret it in charge readout mode. And so this provides us with a dictionary for looking at these different kinds of signals and seeing if there's a compatible interpretation that allows us to put them all under the same umbrella. And that'll be motivating much of what I say from here on out. It's also just intriguing to note that if you were to plot these different excesses in terms of rate versus rock depth, what you see are these bands, which are supposed to highlight different detector materials. And you'll notice that some of these have arrows and some of them don't. So the ones that have arrows are the ones that only enable you to make claims about lower bounds because of higher thresholds. If there are error bars, then those give you an idea of what the total rate is, because these are charge readout. And you'll notice that there's a rough compatibility across different for results based on the same material, and it doesn't correlate with depth in any sort of meaningful way, or at least not way if you were to compare it with, say, the muon flux. And this is, by the way, a plot taken based on a plot in our paper, but it was adapted by SENSEI in April. This is taken from their wine and cheese seminar, and this does include the latest April update. So that's all I want to say about those excesses as interpretations of things that are publicly available. What I'd like to shift towards now is that there's a candidate process that could explain these potentially, and it's worth asking why these haven't been presented as excesses, or at least one interpretation for why they aren't. And it's intriguing to look at a case study. So for example, let's look at EDELWEISS, which has both electron recoil and nuclear recoil data, or just calorimetric versus charge readout. And in both runs, they observe an excess. And so if you wanted to interpret these as due to some same underlying process, there has to be a way to translate charge to energy deposition, because if it's dark matter, it could potentially be responsible, then it would be able to, of course, deposit energy in both of these cases, and you'd like to see whether the two excesses you're seeing could even in principle be related to each other. Is there a consistent description of these? And so what we're looking at in this equation, and I'm sorry, oh, here's my mouse. So E det is, of course, calorimetric energy if we're trying to figure out what the electronic energy is. And there's some function here that is experiment specific, and it'll enable us to perform this translation. And if there's an applied voltage, there's this extra correction term as well. This is the energy per electron hole pair. This is just the unit electric charge, and this is the applied voltage. And one thing that we find is that if you were to interpret the EDELWEISS data as electron recoils, and just plot excess rate versus energy deposited, what you find is that you always overshoot the data. it's not a good fit to the actual morphology. And so this data set can be used to set limits, but not necessarily to claim any sort of interesting excess if your prior is that electron recoils are responsible. So this provides a very bad fit no matter what you do. Conversely, if you were to interpret this as elastic nuclear recoils, something similar is true. So here, what we're looking at in the blue curves are different interpretations depending on whether you look at different variations of the Lindhart quenching model. And what they find is that every single one of these also overshoots the data. And so there's no good fit if you're only considering the conventional kinds of channels that you find in papers that offer interpretations of this. But there's another possibility here, and now I'll be very careful about my terminology because this is something that differs a little bit across communities. So if we're theorists and we're talking about inelastic dark matter, then we typically mean a model in which there's inelasticity on the dark matter side, whereas oftentimes if this is coming from the experimental community, inelasticity means some sort of inelasticity on the detector side. It's a property of the detector, the process taking place inside the detector and not the dark side. And the characteristic feature of this is that when you go back to your dictionary, in relating electronic to calorimetric data, there's an offset, and that offset will change how much charge you get per electron hole deposited. How much energy there is per electron hole pair. And the key feature is that there's this offset term that's independent of the detector energy. And we can see now whether this possibility can give us something that does fit the data. And one example of this would be a semiconductor plasmon. And so these are long wavelength charge oscillations between electrons that typically are much larger than the spacings in between lattice points. And what this does morally is it gives you a different breakdown of charge versus energy per individual event. And so what we found when we thought about this as electron recoils or as nuclear recoils separately is that that didn't give you the right translation between charge and heat. And so it didn't give a good fit that could explain the data for both Edelweiss runs. But now we can see what that looks like if we consider a process that enables us to break the usual relationship between charge and energy that you would typically expect from electron recoils and from nuclear recoils. One analogy here is from electron energy loss spectroscopy. So this is how we typically look at plasmons. So in a condensed matter laboratory, you would fire a semi-relativistic electron through a semiconductor material, and you would observe its recoil as it passes through this thin film, and you would see a characteristic peak at around 15 electron volts. This is a material-specific number, so for germanium, this would be 15 electron volts. For silicon, I believe it would be something more like 17. And it provides a qualitatively different relationship between charge and heat. As the resonant feature that you see here is largely independent of the incident particle's energy. If it's semi-relativistic, this is the way that it's typically probed in the laboratory. And what you find is that when you use this kind of model for translating charge and heat, you can find something that actually fits under the data. So that's very exciting. And if you take nothing else away from this talk, it should be that the kinds of sophisticated materials that we're now using to set these world-leading limits on dark matter below the GeV scale, it's that those materials are made of stuff. And that stuff has lots of interesting collective behavior. It has phonons. It actually has plasmons. It has oscillons. It has lots of different things that we're only beginning to understand in the context of studying dark matter's interactions with materials. That could potentially be related to why we're seeing a variety of excesses that are not particularly well understood, at least at this particular time. And we've thus far been in a situation where the tremendous experimental progress has been outpacing our theoretical understanding of these things. And so this is an area of great need where it's important to understand Bremsstrahlung, it's important to understand the Migdal effect, it's important to understand phonon interactions and plasmons, because what we do find in these situations is that if we just take our naive prior on whether or not these are electron recoils or nuclear recoils, sometimes it might lead us in a different direction than if we were to take into account the full spectrum of possibilities that actually manifest inside these materials. And so we should keep that in mind. And that's a claim that's independent of whether or not anybody believes that the excesses that I mentioned earlier are in any way related to dark matter interactions whatsoever. So now I'll get into the more controversial part of this, which is that if you were to assume that dark matter is responsible, then you would have a number of interesting possibilities to consider. Now, one thing that I am skipping over in this, but people are definitely encouraged to ask, and I have some backup slides if people are interested, is that it's unlikely that you could imagine sort of splitting the difference, assuming that the excesses are real, and that they're due to plasmons, but that those plasmons are triggered by standard model particles, maybe neutrinos from the sun or from neutrons in the ambient environment. That's implausible for a variety of reasons that I don't have time to get into, but I'm happy to discuss them with people if they're curious. So from now on, I'll just talk about dark matter interactions. And I'll break the dark matter interpretation into two categories. So one is direct plasmon excitation, which is similar to how plasmons are studied in the laboratory. So consider a situation in which you have a millicharged dark matter particle. It carries an honest-to-goodness QED charge, and we'd like to be able to think about it in this way because we know how to think about and how to measure in the laboratory charged particles passing through semiconductors. In other words, this enables us to map the dark matter interpretation onto the existing literature for how plasmons are studied in the laboratory. And so we can use the exact spectra, and there's no theoretical uncertainty in how to calculate the event rates. That's the important part, and that's why it's interesting to consider this. But the price that we have to pay is that the dark matter would have to be more boosted than we normally imagine it to be. So this would only potentially be a reasonable interpretation if there's a subcomponent of dark matter that's somehow faster than what we would normally expect from the virialized halo population. And there are not lots of interesting papers that have considered how this could arise. We don't get into that, but let's assume that that's possible. So you have an actual light millicharged particle that's moving faster than normal dark matter. It's a subpopulation, and it's got a long mean free path. So it doesn't interact many times. It only interacts once per crossing. At most once per crossing. Then we can use the electron energy loss spectroscopy literature and scale down the interaction strength, because this is actually what they look at. And we have to keep in mind, though, that in order to actually excite a plasmon, you need a low momentum transfer. Remember, these are events that only arise if you deposit about 15 electron volts into the detector. So you need a forward scatter for a low Q squared. So you need cos squared to be greater than 0, but you also need to be able to deposit 15 eV, and so that puts a lower bound on the velocity that you need, and this is why we're considering somewhat faster than normal subpopulations of dark matter, if such exist. So we need the velocity to be about 10 to the minus 2 or greater. So that's the drawback of considering this model. It has a sort of, depending on your opinion, perhaps unpalatable feature where you need this population to be a little fast. But we can take advantage of the literature on this, because now for a given material, we know exactly what the line shape looks like. We know how to normalize this. And we do a Lorentzian fit using the so-called Froelich model. And so now this is completely calculable, and we can just ask, under what conditions does our millicharge dark matter model give us rates at these semiconductor experiments that are roughly in the ballpark of a hertz per kilogram, and the parameter space is roughly here. So in the context of this model where dark matter is roughly millicharged, what we're looking at here is the red shaded region gives you something that's about 10, in this case, 1 hertz per kilogram for different fractions of millicharges, for different fractions of boosted millicharges. The blue curve is the usual Friesen curve, the same one that Ruben showed in his talk, but this would be the Friesen curve for the total dark matter population that is not boosted. So the picture here is that you produce all the dark matter through Friesen, most of it's cold, some of it's relatively warm or hot, and the warm or hot stuff is responsible for the signals in these cases. Here we've taken the velocity to be 0.1.
A few more minutes left.
Okay, great. So the last part that I'll get to is secondary plasmon excitation. This, I would say, is a little bit more vanilla in terms of what kinds of dark matter models we want to consider, but it does involve a greater degree of theoretical uncertainty because it's not known exactly what the plasmon excitation probability is if you have a contact interaction between dark matter and the nucleus. So the picture here is it's a two-step process. So first, dark matter comes in and it hits an actual nucleus inside the detector. You deposit some 10 eV of energy inside the detector. And just like the Migdal effect, or at least in analogy with the Migdal effect, the energy deposited into the nucleus is what excites the plasmon. So you have a plasmon excitation that's a secondary effect from the nucleus getting an energy deposition from a passing dark matter particle. Now, one thing to note is that there's this very nice paper by Tongyan Lin and Jonathan Kozachuk shortly after ours, which pointed out that you could actually calculate this in a particular situation where you produce a single plasmon in association with a nuclear recoil, and the nuclear recoil is treated as though there were a free particle dispersion relation. An important thing to keep in mind is that our interpretation is a little bit different than this paper, because we're assuming that you get the signal by producing lots of phonons in association with a single plasmon, because the typical dark matter particle won't have enough energy to liberate a nucleus from its lattice site. And so the picture here is that the dark matter deposits a certain amount of momentum into the nucleus, but the nucleus can't leave its lattice site, and so there are lots of phonons. It's not a free particle. It oscillates as though it's an oscillator potential, but it can still trigger a plasmon excitation, and that's where the energy and momentum are carried. So it's qualitatively a little different, but unfortunately harder to calculate because this hasn't been studied, although we're working on this. So just to compare this with the earlier interpretation, here we can use 100% of the dark matter, we can use the normal virialized velocity distribution, but we can't calculate the plasmon excitation rate, so we have to fight with one hand behind our backs and parameterize our ignorance with some ansatz here, and so we'll consider different possibilities for what we could do depending on what that probability is. And so normally what we would have if we were looking at the proton cross-section, because we're now thinking about nuclear recoils, plotted against dark matter mass, is that we would see a plot like this. Here, if you say have a dark photon or something that has equal proton and electron couplings, this is what the parameter space would look like if we were only placing limits, despite the fact that there are lots of excesses in all of these experiments, or all the ones that are dashed. And we were translating electron recoil results or photoelectron results onto, or typically these experiments, for example, SENSEI and DAMIC typically present results in terms of the electron cross-section, but we can translate these into a proton cross-section on the assumption of equal couplings. But since they do have excesses, under our different interpretation, which requires a different prior, we have a favored region. And the reason, the favored region here for different assumptions of what the total rate is and for what the plasmon excitation probability is given in the shaded region here. It stops abruptly. Oh, excuse me. It stops abruptly at one point because if you're too slow, you can't excite a plasmon of 15 electron volts. Because here the picture is that you put very, very little energy into the nuclear interaction, and that's sufficient to excite the plasmon, but it doesn't make the nucleus recoil in a way that would be detected by other means. So the name of the game here is to see whether there's a sensible model that would fit this parameter space for a given ansatz for what the excitation probability is for plasmons. And it actually turns out to be everyone's favorite model. It's a dark photon. It's but now a massive dark photon. And one that lends itself to an interpretation in the context of thermal freeze-out or potentially asymmetric dark matter, and something that could have accelerator follow-up. So now we've added other bounds onto this parameter space, but you'll notice that some of the favored region does overlap with the thermal relic curve and is in the place where future accelerator experiments, B factories, and fixed targets like Bell2 and LDMX can definitively say something about this, but just keep in mind that this is only one model. The only thing that's necessary for this general interpretation to hold is that dark matter scatters a nucleus with a certain cross-section. So it's just fun to put it in the context of a larger model, but we shouldn't take this particular one at face value. We can have other ones too. So I'll leave it here since I'm out of time. And I'll just say that if this interpretation is sensible, if it has something to do with dark matter, then future results should continue to see order hertz per kilogram excesses. Reuven mentioned in his talk, and this is the first time I heard about it, that SENSEI thinks they understand what their excess is, and that we're very excited to learn more about that. If that's true, then that has some pretty bad news for this interpretation. But there's a general point here that goes beyond the excesses. The excesses are intriguing and they motivate us to think more rigorously about what could be happening inside these materials. And if you take nothing else away from this talk, take away the fact that as we go to lower and lower masses in studying dark matter, and we go to lower thresholds and invoke more exotic materials, and we'll surely be seeing lots more of these in future years. We'll be seeing Dirac materials and so on. We should keep in mind that lots of interesting phenomena might present itself in very different kinds of ways depending on what kinds of effects they're exciting inside these materials. This isn't just vanilla big particle recoiling inside the detector territory anymore. So I'll leave it there. Thanks.